Yeah, we'll start in a few minutes when everyone is here. While we're waiting for everyone, any questions about next week midterm? Any concerns? Anyone wants to ask anything? Okay. Yeah, the midterm is going to cover pretty much everything that covered, including this lecture in the course, right? Including register allocation. Probably more heavier towards the beginning than the later part. But anyway, anything can be part of it. Right, we expect it to be on Quercus as of now. So I think by now you should probably wrote some tests with Quercus and should have no issues with uploading files. Remember, there would be some problems that are just multiple choice questions, but some would require for you to upload images. You can upload whatever way you like. You can draw and then upload. It's all up to you, but make sure that you know how to do it on Quercus, so it won't be a surprise for you. Most students by now should be able to do it, but yeah. We don't share the past midterms, not to make things more complicated, because it's like a, army race in a sense that if you keep sharing the previous midterm, because that's already gone, we need to come up with more and more complicated problems, right? But what you should expect, we're not gonna share, like Bojan might have shared some, problems, but essentially you weren't gonna see anything that would look different from the lectures, right? So you're going to do data flow problems, control flow, all the usual things, whatever we covered in the lectures. So there won't be any surprises. Historically, we had a very decent average for midterm, so there's no need to make it more complicated or less complicated, right? It won't be longer than 90 minutes. So the specific time we'll figure out, but definitely won't be longer than. So it's not going to be the whole 2 hours. It's going to be somewhere between 80 to 90 minutes, I would expect. Any other procedural questions about midterm? Okay, if not, then we should start. So today we're going to talk about register allocation, one of the most perhaps theoretical parts of everything we cover. So they're gonna problems that are really usually attributed to the CS theory parts, such as coloring and analysis of the graphs. This is one of the places where systems aspects of compilers are very tightly coupled with theoretical background. So you can't really do very well on those topics if you afraid of theory. So if you're not as comfortable with theoretical things, please ask questions. Make sure you understand everything. Okay. Okay. So, and this is a very fundamental thing. Like you can't imagine any compiler that won't have register allocation, right? This is like a seminal thing for every compiler. So, what we're gonna cover today is we're gonna talk about register allocation and coalescing. That's the first lecture. A part of the lecture, we're gonna be doing some introduction. We're gonna abstract out the problem or describe what the problem is and what the right abstraction for it. We're gonna talk about the algorithm, the main algorithm, then how to add a required feature to it called spilling, and we're going to talk about register coalescing afterwards. And this is a reference for the potential extra reading you can do if you want to go deeper into this topic. Okay, so what is the motivation? Well, as of now, everything we've seen was some pseudo registers, right? We were using them at our discretion. We were calling variables x, y, or v0, v10, v100, right? But at the end of the day, all that nice abstraction has to find some place in a real hardware, in hardware registers, right? In a real procedure. And obviously that means you have to do this mapping, right? It's extremely register location. You can call it an optimization, but it's really a key for success of the performance, because if you don't place things well in registers, you're going to go to memory, and accesses to memory are 1 to 2 orders of magnitude slower. So essentially your whole performance will drop down dramatically. So when registers are inefficient, register allocation is inefficient, there's a huge performance penalty. So it doesn't affect correctness, but it does affect performance quite significantly. Register allocation can be useful for some other optimizations, such as common abstraction elimination, as we will see later. So essentially, the goal is very simple. Given the piece of code, right, that you generate through all your previous optimizations, find the allocation for the all pseudo registers, if it is possible, given a certain register budget. If there are no enough registers in the machine, hardware registers, we need to choose some registers to spill to memory, right? There is no backup here. It's not like, in theory, we say, oh, this graph is not like, for colorable, so we just give up. You have to generate the code at the end. So you need to find, then you have to keep spilling up until you still color, right? Like, so there is no like, you can just simply give up. You always need to produce some register allocation. So let's look at the example. And the question I have to you, there is a small piece of code here, right? Our traditional hammock. So you had pseudo registers A, B, C, and D. And the task here is to find an assignment without spilling with only 2 registers. So I suggest you guys to try it out on yourself, either on your computer or on a piece of paper, and tell me what that assignment would be and how would you do it. It's a very simple problem. You can do this manually. But I want, through this lecture today, I want to get a feel of what is to do the register allocation. You'll see how quickly it can get more complicated. But let's start with this simple problem first. So try to assign the registers, right, such that you don't break the correctness of the code. And I didn't define it. What does it mean? I want to get your intuition. I want to see whether you can intuitively reason about correctness here. So only 2 registers. You had 4 variables. You need to assign 4 variables to 2 registers. You can call register whatever you like. It doesn't matter. You either, whenever you're ready, you can either talk or post it in the chat, whatever you're more comfortable with.
Just a quick question. The
Yes.
dot in B and C, is that denoting that there's some arithmetic happening with A?
Yeah, it means you don't need to care. So like it cannot be just assigned something that doesn't affect your allocation. It's constants. It doesn't matter. What matters, there is a depth and use, right? So, but you don't need to worry about the dot part.
Okay.
You don't have any progress? Okay, I'll wait for a few more seconds, but I was hoping someone's going to propose something. Anyone wants to try?
I can try, but I don't know if I'll be correct or not.
Yeah, go ahead.
So let's say we have register R1, R2.
Yeah.
And then, so first of all, we have assignment to A. So that will be like A assigned to R1.
Yes.
And then let's say we're going to left block. So B is equal to something else. So B is assigned to R2.
Yes.
And then we used A. So we use a value in R1. And then D, since we don't have any other A we can replace, I am assuming we can replace
Yes, you can.
the assignment for D to R1. And then later we use B plus D. So we'll put that into either R1 or R2, I think will work.
Well, you need to keep, so essentially if you, for example, if you make D and A R1, so then D would be R1 there and B would be R2. So after you pick those things here, you cannot make any selection here, those stuck, right? It's like this is, say this is R1 and this is R1. This has to be R2. So this is R2 plus R1.
Okay, I see.
Like you have no choice here. This is just has to respect it, right? How about this branch?
I think it's basically the same thing. Yeah, instead, for B, you just substitute everything else for C.
Yeah. Okay. Yeah, so essentially the key idea, you put A and D in one register and B and C in another register, right? And I built something that will later formally define an interference graph that tells you things that had an edge, which means they coexist in time and space at the same time, right? It means they cannot have the same register. So like, for example, A and C, they overlap here, right? I cannot use them the same register because this A here has to be what A is here. I cannot make this being redefined, right? So this means there's an edge here. So this graph has essentially this structure. So we make some assumptions, of course, here, right? So we make an assumption that there is no use of A here at the bottom, and only one of B and C are used, because otherwise, if we need both B and C, that won't be true, right? We need to keep them in separate registers. So those are the assumptions we make, but under those assumptions, we essentially assign the registers here. So you see, there was 4 registers originally, but we only need 2 physical registers for this simple graph. You probably get a feeling that this is there's not a trivial task to do, right, on the code. Assigning registers, the more complicated the code, more tricky it will be. So it is indeed a very challenging task, and very soon the theory will show us why is it so challenging. So let's now go to the problem and try to define it first intuitively, right? And I hope when you try to do this example, you got a little bit of that intuition on your own. So essentially, 2 pseudo registers interfere at some point in the program if they cannot both occupy the same register, right? So if there is a piece in the program where they cannot be both the same thing, that means they interfere, right? An interference graph is something that we try to build by looking at the code. So interference graph then essentially formally is an undirected graph where nodes are pseudo registers, and there is an edge between 2 nodes if their corresponding pseudo registers interfere. That's why it's called interference graph. So yet another graph that you have to deal with in compilers that helps you with register allocation. Okay, any questions about the definition? Okay, this graph is going to help us a lot. This graph represents the interference, but it doesn't represent some other things mostly because it's very non-trivial to do it. First of all, it doesn't represent the extent of interference. So 2 things might overlap by just 1 line of code, or might overlap by 100 lines of code, right? So the extent at which they interfere is not represented, right? You only know it's just a binary, yes or no, interfere or not interfere. And it also doesn't say where in the program there is interference, right? Again, this is binary, so it's not very accurate representation of the interference information, But that's a good starting point because it really tells you where it's safe to do it, right? So it might be not accurate in the sense that it might be conservative in some decisions, but it's still going to be accurate, right? Is this part clear? So whatever we're going to use, like interference graph representation, the first representation should be good enough to start. Even that would be quite challenging to solve. So we don't figure out difference between interfere many times across many different places in the code versus just once. Cold versus hot, we also don't make that distinction because soon you will realize that it matters where there is interference, but at the beginning we ignore all of that. Okay, so what we do next with this graph? Well, I will come back to the definition again. Hopefully you learn it in one of your theory class. A graph is called n-colorable if every node in the graph can be colored with one of the n colors such that two adjacent nodes do not have the same color. So essentially assigning n registers, where n is the number of physical registers you have, without spilling is essentially coloring an interference graph with n colors. So we need to assign the node to a register, which we just call a color for simplicity. That node to adjacent nodes assign the same registers colors. So there are definitely some questions that come. What if I can't do that? Is spilling necessary or not? How I know is the graph uncolorable or not? So those questions are actually related. And one problem in some way is that we know that general solutions are not very practical, right? To determine if graph is n-colorable is an NP-complete problem for n bigger than 2. That's what theory tells us. So it means doing it in a, stupid directed way would be very expensive, right? Impractical for most graphs. It means we'll have to use some heuristics, some heuristical algorithms. So most register allocation algorithms vary in complexity. Like some of them are as complex as n cube. Let me ask you some tricky questions. So what is the minimal theoretical, like the top complexity is NP complete, but what is the minimal possible complexity should be for any register allocation algorithm? So what is the bottom? Actually, bottom is reachable. There are algorithms that can do it in that amount of time, but what is the minimal complexity of a register algorithm has to be? Something that you cannot beat. Any theories? So how? Okay. Well, essentially, yeah, so it's linear. So you need to attend every node at least once, right? You cannot color without being at that node. So it has to be linear, and there actually exist some heuristical, not particularly efficient, but heuristical algorithms that are linear in time, right? So people still use them, right? So the range of complexity from what I've seen in my personal experience ranges from linear to cubic. So this is the range of algorithm I've seen. Okay, so let's go now that we define things. Let's look at interference graph and how we build it. So we need to refine the notion of a node and finding the edges. This is the first two steps in building an interference graph. And when we do coloring, we would use heuristics to try to find an uncoloring, right? A success with coloring using our heuristics means we found an assignment of registers. A failure might mean two things. Either graph is not colorable or graph is colorable, but it's too expensive for us to find this. So we need to do something else, okay? We can't just fully give up. So we need to do something, which is spilling, right? But that's what the original algorithm will do. So let's look at the nodes in interference graph. So the first thing we do is by looking at this, this piece of code, we need to make a decision about their interference graph. For example, here, if we have A equals to here at the bottom and then A again here, you see this might, create this whole line of dependency of using the same register. And the question is, does that make A and D interfere? Because if A and D interfere, right, then it means this is not too colorable anymore, right? You have to add this edge. So this is the question that comes up here. And the answer to that, should we have an AD edge? And the answer is no, since even though it's called A, it's a completely different A that has nothing to do with this A. So you don't necessarily have to use the same node and the same edge. So essentially the way we handle that, we define something called live ranges and merge live ranges. So let me define it. So the motivation is to create an interference graph that is easier to color. So that's why I defined these new ranges. So what we try to do, we try to eliminate interference in the variable's dead zones, the places where it really doesn't act, which is like a fake interference, and increase flexibility in allocation so we can allocate the same variable to different registers. A live range essentially consists of a definition and all the points in a program in which the definition is live. So how we can compute the live range? Well, essentially we can just overlap the existing live ranges. So for example, if we have assignment A here and here and the use here, we can just overlap all of that together into same way. And it turns out, if you want to define live ranges, you actually had all the machinery needed for that. You had something called live variables, and you had reaching definitions, you know how to find those. And what you have to do is essentially, given all this information here, already colored everything for you for each instruction. What you can do, if you see this thing for D1 and D2, coming from two different edges where D1 and D2 actually has the same thing, it can be merged, right, into the same D, right, because it's not really different across those different edges. So essentially what merging of the live ranges does, it starts by putting each definition into a different equivalence class. And then for each point in the program, it checks whether the variable is live. And then if there are multiple reaching definitions for this variable, then it merges the equivalence class of all such definitions into one equivalence class, right? So that's essentially what happens there. Does this process sound familiar to you, to anything we did in this course already? So this process of the live merging live ranges, does it look to something, it's not called the same way, it's actually had a very different name, but does it sound conceptually something similar? Like we look at all these different defs that reaches one point, and when they merge them into one equivalence class. There was something that we learned recently that actually should sound very familiar. Anyone? Again, the name is very different and the context is different, but the meaning is very similar. Okay, you can think about it. So I'll finish with some definitions. Is those merge live ranges. Usually we just call it live ranges for simplicity, not to call them merge all the time. And usually in compiler architecture literature, they call VABs. And one last time to say what it looks similar to. Okay, SSA, right? 5 functions. So essentially what happens is that if you see, now you see why it's actually not necessary to implement a 5 function. Essentially 5 functions and SSA variable is simply a merge live ranges, right? If there's not, like when you see something like x4 equals to 5, x1, x2, x3, this is nothing other than the merge live range of all these variables, right? It's already there. So essentially, when their SSA reaches the final stage, right, of register allocation, and there is no way 5 nodes can exist beyond that point, right? Because you cannot map them to anything. What happens to them, they just become these live ranges in the register allocation algorithms, and 5 functions are deleted, right? So essentially they keep all the useful information you need to have, it's converted into something useful, and then completely deleted in the code. So it's very easy to handle. So essentially now you can effectively convert it back out of SSA form, right? And you get rid of all the 5 nodes, right? So at that point. Okay, so this is the live ranges, and essentially when you're gonna think about SSA representation, all this live information is already there. Like you don't need to build the new live ranges, it's already represented by your SSA form. So then we need to define edges to the interference graph. First, we found nodes, right? Nodes are those live ranges, right? Merge live ranges or BABs, right? Then for each of these ranges, we need to find whether they interfere with each other or not. Intuitively, it means that if they overlap at some point in the program, they interfere. So the algorithm, at each point in the program, we need to enter an edge for every pair of the live ranges at that point. So what we need to do, we go through each line, we see, oh, these 2 ranges interfere at that point, they should have an edge if they don't have already one. Obviously, an optimized version wouldn't be doing that at every line, right? It's only going to do this at the start of each live range. Why is that okay? Why I can only do it at the start of live range? Why I don't need to do it for every single line of a live range? Only at the beginning of the live range. So imagine there's one live range, another live range, they overlap, right? I could go through every single instruction in each of these live ranges and say, do we interfere, do we interfere, do we interfere? What I claim is there's no need to do this. I do it only at the beginning of one, at the beginning of another one.
Because that's where the variables are defined?
And this is where there are changes, right? That's one variable is starting versus definition, right? And after that, nothing really changed. There's uses afterwards, right? So there's a def there, right? Def here, right? And the def changes, this def changes something. And in between, there's just uses. They don't really change anything, okay? So instead of going through like potential 100 of instruction, you just look at the beginning of each live range. So it's faster and gets a better quality information. There is one also caveat that I had to always bring up, that the information is not fully accurate. It's conservative. For example, look at this piece of code. You had if Q go to L1, there is A here, B here, and A here, B here, the use. So does A and B really interfere or not, is the question to you.
Is Q a constant?
Yes, Q, you can assume it's a constant predicate. Or for whatever matters, it's a thing that independent from A and B.
If Q doesn't change, that I guess A and B do not overlap.
You're absolutely correct. So if you're smart and you understand the predicate knowledge, and your algorithm is path sensitive, you could say this can go into 2 different registers. Live ranges are not that smart. The way the line ranges are stored, they're stored this way, right, in the code. And what's going to happen, they're going to report that as 2 overlapped live ranges. Okay, so something I want to highlight to you, right? So they're going to see it as a place of overlapping, right? And because of that, they can't really ignore that information. So remember, the information is conservative, right? It's not going to miss anything, but it might make, you know, some false overlaps. So you had live range for A, live range for B, and this live ranges overlap at this point. Okay, after that, we need to do coloring. So reminder, like multiple times today, I'm going to remind you that coloring for n bigger than 2 is NP complete, right? So how can we handle such a complicated case? Well, there are a lot of special cases. First of all, remember the registers you're going to get in practice is going to be like 30 or 20 or like substantial number. So there's highly likely that you're going to have a lot of nodes that was degree less than n, right? So they're not overlap that badly. So if a node was degree less than n, you can always color it successfully given its neighborhood colors. In fact, it doesn't matter what its neighborhood colors are, because the degree is less than n, it means there was at least one color that was not used for anything, right? I can always color that node. So if the node with degree is equal n, then we can only color it if at least two neighbors share the same color. That's another heuristics. And if a node has degree less than n, well, sometimes we can color it, sometimes not always, right? That's the problem. So this is one example of that. So for example, here, each node has degree n equals 2, right? And we can still color it, but there is no guarantee. Okay. So what's the first simple coloring algorithm we do? We do a simple algorithm where we pick a node with degree less than n, and we remove the node and its edges from the graph, from the interference graph. Why we can do this? Because none of these nodes affect coloring. I can safely take this node out, remove all these edges out, right? Because I always know I can color it later with some color. There's no problem with it. And then we keep adding things until the nodes are left. And then we do a reverse process and add colors. So here's an example with n colors we're going to do now. But the question's for you. Why this algorithm has any benefit? Like why I can color something by just doing that? If there might be some nodes with degree equal n or more than n. So why this strategy might work? It's a very simple algorithm. I take whatever has degree less, I remove it with all its edges. Next one, remove it, and remove it till I can do. Guys, it's very simple, because every time I remove the node, I remove some edges. These edges belongs to some other nodes. I might reduce the degree of some other nodes. They might have higher degree, but as I remove the nodes, I reduce their degree. So I might ended up just color everything. So for example, for this graph, look here, n is equal 3, right? So what I'm gonna do, I'm gonna just, do the regular stack thing. I'm gonna start with B, then C, then D, then E and A, right? Like B has just 2 edges, less than 3, then I remove B, then after I remove B, I can do C because C just lost this edge, right? So C now can be the second one. Then I look at D that has just 1 edge, I can put it in here, and then I can do E, and I can do A. So the key here, you see there were 2 nodes here with degree equals 3, that equals the number of, colors. So you cannot just blindly color it like in a straightforward manner, but applying this algorithm, I get the order and I just can go and assign the colors. And then that's my stack going from B, C, D, E, A. And then I color in the reverse order. So I give A red color, then I give E blue color, and I give D like orange or yellowish color, right? And C and B get whatever I want to take because they had a way to get a color now, right? In a non-interfering color. We have a guarantee that it can be done. So the key idea here is the degree of a node may drop in an iteration, and we try to avoid making arbitrary decisions that make coloring fail, right? So it's relatively straightforward algorithm. So it's not perfect though. So we might need to we might need to deal with some heuristics when coloring fails. So for the first step, we build interference graph. We iterate until there are no nodes left, and if there exists node V with less than an n neighbors, we push it. There's node V on register location stack. If there are not a node left like that, we return that says heuristic failed, right? So it says we cannot continue, right? And If we reach the end, we remove V and its edges from the graph. Then we do assign registers, which is very simple as well, right? So what does the coloring really accomplish for us? So if we finish with the algorithm, we are done. We are colorable. We also obtain the assignment. Just use the colors, give every color a register, and we are done. What if we are stuck? Is it colorable or it's not? Well, the thing here is that colored successfully means we got an allocation in a register. If something is not colored, so we're stuck somewhere in the middle, it means the non-colored register can now go into the memory potentially. So since it has to stay in memory, we have to put it in the memory, but there is a cost to that. Depending on what we put in the memory, it might run frequently or infrequently. Imagine I would put something in memory that is in the middle of your most hottest loop, like, I don't know, 10 nested level loop, and it's in the middle of this loop. I'm going to put this into memory. So instead of that taking 1 cycle, it's going to take 100 cycles, right? That's a huge penalty. So essentially, when we try to decide what to leave in memory, we try to look at, some cost, estimate the cost of them. So we look at the proportional to the number of users definitions. We try to estimate its loop nesting, and the objective here is to minimize the sum of cost of uncolored nodes. So there are some heuristics that people propose it. Remember, we not always perfectly know at compile time how long each loop takes, each instruction is going to run, right? That's all estimation. So one heuristic that benefits of spilling a pseudo register is we try to increase colorability of pseudo registers if it interferes with, with too many things. And we can try to approximate the degree in the interference graph for different nodes. And there are another heuristics called greedy heuristics that try to spill the pseudo register with lowest cost to benefit ratio. So whenever spilling is necessary, right? So, so we try to always reduce, we spill something that has the low cost for us and the highest benefit, right? So that's what we want. So spilling as a technique obviously depends on the hardware that you're operating with. In CISC architectures, something like your Intel, typical Intel or AMD processors that you use, they can operate on data in memory directly. So the memory operations obviously slower than the register operations, but it's similar instructions can use them. In RISC architectures, which is an example, is your ARM processor that probably your cell phones are using. So the machine instructions can only apply to registers. It means you would need to generate extra instructions, right? Not just, extra access to memory, but the instruction the same. You would need to generate extra code. And essentially, the use must first load data from memory into another register. So it means I need to have some registers always handy for spilling, right? Because I need to load from memory into some register and then use it. So even if spill to memory needs a register at the time of user definition. So usually you would reserve some register for those types of operation. Okay, any questions so far? So you got so far, we defined the interference graph. We look at some heuristics and how to color it, right? If it's colored with this heuristics, we are done. If not, we need to do spilling. So we're trying to figure out how to do spilling efficiently right now, right? So remember that you had, if something stuck, it doesn't mean that you had to spill just at that register. It means something is not colorable. I need to find something somewhat optimal to spill, right? And the cost of what to spill is very different, right? I'm essentially going to take an instruction and replace it with either a more costly version of that instruction or extra instructions, but they all going to go to memory. So make something that was 1 cycle or 2 cycles and make it 100 cycles. And it can have a different pieces of your code. If something bad like that should happen to your code, you want to pick the place in the code that where this will be the least painful, right? Probably not in the deep nested loop, right? Somewhere outside. Okay, So how we identify the spilling? Again, we build an interference graph, and then we iterate until no nodes left. And if there's exists a node with less than n neighbor, we place V on a stack to register allocate. Else, if we don't have, then we put a node with highest degree to cost ratio and mark it as spilled and remove V and its edges from the graph. So essentially, whenever we're stuck and we see something that's not colorable, we pick a node that has the highest, benefit of spilling, lowest and try to make sure, we always try to remove the node with the highest degree, right? Because the higher the degree, the more problematic is the coloring of this node on average. And that's a heuristics, and then we divide it by cost. And remember, spilling may require user registers, changing the interference graph. So after you do this thing where, say, I take a node and spill it, you cannot just use existing interference graph. You need to reiterate over the graph, right? So essentially, you need to recursively redo the interference graph, rebuild it, and perform the step above again, right, until it's done. And then after that's done, we assign the registers, and until stack is empty, we remove things from the stack, color it, and all its neighbors. So it's straightforward, right? So this algorithm, while not optimal, obviously, it's all heuristics, would make sure always that you get some assignment, right? So at the end of the day, you're going to spill as many as you needed, and you're going to get, you're going to look, and if there's no node with degree less than n, I'm going to keep spilling the most the ones with a large degree. Eventually, I'm going to spill to the level where I can color, right? So this is the most straightforward strategy. But obviously, the question is, what should we spill? And there can be strategies that actually, competing. So sometimes we want to eliminate something that gives us a lot of interference, right? Something that has a very intuitive, a very long live range, right? Something that live across the whole big piece of the program that interfere with many things. It's a good candidate for spilling, right? Because it adds a lot of edges to me, right? I want to remove that, but that only from the coloring perspective, ignoring the hotness of the code. What is also important, how frequently whatever I'm going to spill is executed. If it's in the middle of the very important loop that might try to avoid it, I would better spill something peripheral to that node. Maybe something that is live across a lot of call functions. That's another good thing to spill. So one heuristics that people use, they had a function that defines a cost, which is somewhat weird function that but that's something people define. So for example, the cost was defined as the number of devs and users, right? That's the cost. The more devs and users, the more costly you are, multiplied by the 10 to the power to the loopness depth. And that divided by the degree of the node. Okay, so this is something people use as one of the cost function. This is kind of an assumption here that you had that the loopness depth make you exponentially more important the deeper you go. Because usually, traditionally, there is an estimation that if there is a loop, it's running for a non-trivial amount of iterations on average, right? Typically, that's the way we write code. Of course, it can be 1 million iterations or something, right? But you can't know without profiling, so you had to assume something. So they just had an exponential thing. Remember, this is heuristic. So essentially, using these heuristics, you can apply this algorithm they call Chaitin's algorithm. One problem with this algorithm that is giving up very quickly. So essentially, this algorithm works like that. The minute it sees, oh, I cannot find anything, it says, let's do spilling, let's do spilling, let's do spilling, right? So that's what it does. One optimizations you can do, for example, if you're going to deal with this thing and apply this algorithm, it's just going to give up relatively quickly with n equals 2. So one optimizations you can do is prioritize the coloring. So you eliminate the nodes and its edges from the graph, but you don't call it spilled yet, right? So you delay your decision on spilling. You just said, you know what, that can be a good candidate for spilling. I'm removing it because it's breaking it. But then maybe as I'm going to spill other things, right, that thing will fix itself. So that thing, when I come back, might not need spilling. So essentially, it's kind of opportunistic. I know this is a candidate for spilling, but I'm not going to spill in yet. I'm going to keep spilling more. And when I'm going to do color backward, maybe on the backward pass, it turns out I can color without spilling this guy, right? So you don't commit to spilling yet, you delay the decision. So you don't commit to spilling right away, you try to color again in the assignment phase. Remember when I go through my stack, as I form the stack, when I start to assign the color, I will try to assign the color first. And if I can do it without spilling, I won't do spilling, okay? So don't give up, don't commit to spilling right away. So it's like a hard labor. If someone asks you to do some heavy assignment, you typically try to delay it, that maybe someone else will do it, so it would be easier for you to do. That's the same thing. It's like a lazy approach. Okay, so how we do split live ranges. So remember that splitting pseudo register into live ranges to create an interference guards is makes it easier to color. So essentially what we can do, we can eliminate interference in a variable dead zones, and it increases flexibility in allocation. So for example, we can allocate same variable to different registers. If you look at the code here, you have A here, right? And A here. So one thing you can do, you split the live ranges by using variable A1 and A2 for A, right? So that splitting would make your interference graph easier, and it would be easier to color it. So you had, it's a non-trivial trade-off, as you can see, because I add more nodes into the graph, right? But this graph has now lower average number, the degree of the nodes. So the degree of the nodes reduces. That's what's important. So this is one trick you can do, splitting the live ranges. So the key idea here is that split a live range into smaller regions by paying a relatively small cost to create an interference graph that is easier to color. And that eliminates interference in a variable's nearly dead zones. This is a dead zone when there is, like you see, this zone for register A is actually a dead zone because you don't need A here, you don't need A until here, right? So it's a dead zone for this variable. So you don't really need to interfere with D. It has a cost. You would have to deal with extra memory loads and stores at boundaries of the region where there's no activity. But the idea is that you can allocate same variable to different registers, and that can be useful. So even though it sounds counterintuitive sometimes, why I would place the same variable to different registers, what I really do, I try to make something that contiguously is very heavy into smaller areas. And the fact that I'm using two different registers for that might avoid a lot of complications with other registers. So I'll show you a few examples where that would be more clear. So I will show you one very canonical example from the loop where I have variable, one for loop and two inner loop over J, right? And there is variable A and B where I accumulate the sum of the element. And there is no use of B here, no use of A here. So these two loops are really independent from each other. And this is another example where you clearly see there is an interference here. So this trick you're going to see here is quite interesting. So first of all, if you're just going to naively apply the algorithm here, you're going to have A, B, right? And I and J, right? And your interference graph looks like crazy, right? Everything interferes with everything, right? So there's no way you can color that, right? With n equals 2. So that's a challenge. And that graph is another classical example, which is not too colorable, right? So A, B, and C, you see A interfere here with C, A interfere with B, and B interfere with C because B plus C is used at the same time. So everything is like that. So none of that is too colorable, right? If you don't do anything. But what can you do is essentially you can create an artificial variable A1 here, right? And assign A1 to A at the border of this block. So and then you use A1 here instead of A, because really these two things has nothing to do with each other. They can be different names. Why does this help? Well, the variable A, in a sense, gets two registers, right? Two different colors right now. But it helps with interference between B and C, because one part of A1, one part of the register kind of live range only interfere with C, and another one only interfere with B. And that's what we exploit here. We make sure that we make A two different instances, and we make them interfere only with what they want to interfere, but not with the other one. So sometimes you can make things more complicated, but then it makes other things easier. And this graph now can be two-colored. Okay, you see what we just did. Okay. Okay, where we are right now, we're almost at the beginning. We'll just formulate a few next steps and continue in the next hour. So we essentially need to formally define where we do splitting. I show you a set of tricks, but we need to formally add them to the algorithm. But you hope you follow me so far, right? You've seen we start with the coloring, then the basic coloring might fail. We added spilling to it. First dump spilling that just spills every time whenever something there is a problem. If there is, then later on we say, well, we don't need to do it all the time. We can delay the spilling. We can also be smart about when we spill. And we also now try to fix to avoid spilling in some cases with some tricks like live range splitting. So we need to answer those questions to figure out this in a general case. When do we apply live range splitting? Which live range to split and which doesn't? Where should the live range be split? You see there are so many dimensions here, and how to apply live range splitting with coloring at the same time. So advantage of coloring that it defers arbitrary assignment decisions until later. So remember when you assign colors, you had some freedom on where to assign colors, right? And sometimes that random choice is better to delay until very last minute. If you had a freedom, you don't want to lose this freedom. You want to keep the freedom as much as you can, right? So you try to defer those decisions. When coloring fails to proceed, you may not need to splice line range right away. You check whether degree of a node is bigger than n. It does not mean that the graph is definitely not colorable, right? Remember. So because interference graph does not capture position of a live range. So one observation you can make is that spilling is absolutely necessary if number of live ranges active at a program point is bigger than n. If there are a number of active instances, if it's a real, not a dead zone of a variable, active real def use areas, and if it's bigger than n, then spilling is unavoidable. There is nothing you can do here. And if that's the case, you can just do apply live range splitting before the coloring here and identify a point where the number of live ranges are bigger than n. And for each live range, active point around that point, you find the outermost block construct that does not access the variable, and then you choose a live range with the largest inactive region, and then you split the inactive region from the live range. So essentially, what you do, you find the places in the code where spilling is unavoidable, and that's going to be a very costly operation, and only there you apply the live range splitting, trying to avoid the spilling. Okay. So you pick those places and you apply it there. It's very simple in terms of in the way it's done. You just add an extra variable, right? An extra copy, right? And then you do it, okay? Let's have a short break now and we'll continue from the slides in 10 minutes. Any questions before we go into the break? Okay, so see you in 10 minutes. Okay, let's come back for the second hour. The people who were able to turn on their cameras before, please do so again. It's very helpful. Thank you. I use this opportunity now to handle any questions you guys have. So I try to reiterate multiple times. I understand that the whole process is not that simple, right? You know, people work on register allocation for like 50, 60 years, right? There's a whole lot of theory built on it. There are a lot of PhD theses written on this topic. We were right now covering just the very basics, but hopefully after that you would understand why register allocation is such an important piece of every compiler, right? And such a non-trivial thing as well. Any general questions? I understand you might not understand every little detail on what I do, but you can always, you know, iterate and ask. At the end of the day, in practical assignments, you will be asked to do relatively simple tasks. Coloring can be done in a relatively straightforward manner. We're not going to give you a crazy, you know, graphs to color manually, but I want you to understand the general concepts and optimizations on it. Okay, any questions so far? Hopefully you're not all fully lost, so you still understand what I'm doing, right, with the coloring. Okay, so you see, we always use some form of heuristics because the general problem is very hard to track. We now can always color with splitting, with spilling, and some spilling can be avoided by using splitting, right? And we usually try to split the inactive regions from the live range. So those dead zones, so-called dead zones, that informally where something overlaps just kind of artificially by construction. So in summary, what we just achieved in the last hour is we look at the problem of register allocation in a machine with n registers. We are trying to avoid spilling where possible. We do it when it's required. We find an assignment for all pseudo registers whenever it's possible. Our solutions based on several general concepts and several optimizations to it. Our key abstractions is the interference graph. Remember, the nodes are our live ranges, also called merge live ranges, that had a lot of nice similarity to SSA representation, as we figure out. The edges is the presence of live range at a time of definition. So if two live ranges are live at a certain point of time, the same point of time in the code, that means they had an edge. Then, using this abstraction, we can do register allocation and assignment, and we try to essentially approach a problem that is NP complete when we try to do n colorable for n bigger than 2. And since it's NP complete, we have to use different heuristics to make it tractable. So in our process, we claim the graph being successful to be colorable because we automatically get the assignments. We use a heuristics, not heuristics, we use an observation that when the node has degree less than n, it can always be colored. So we always start with those and delete them from the graph, trying to reduce the degree of other nodes. If it's not successful, it's colorability unknown. There's no assignment, but we can essentially do spilling for those. And then we show you how to reduce the amount of spilling, right? So spilling is always can make it possible, but excessive spilling would have a tremendous negative effect on your performance. So I show you several tricks, such as delaying the spilling decision. So remove the node, but don't claim it's spilled yet. Let it finish, get the stack, and when you color, use that extra freedom you have to potentially avoid spilling some of those registers. And another technique is splitting. So splitting can potentially avoid spilling in the live ranges where if the live ranges has high degree, just because they have these little dead zones where there's an overlap, that can be avoided with splitting. Remember, splitting is not free, right? You would have to add a new pseudo register, and that register would need to get a different color from the original one. So you make A, something like A1 and A2, and they had 2 different colors. Right?
Question?
Yeah.
You just mentioned splitting. So I was thinking like if we are already in SSA, then there is no point in splitting at all. Is that true?
Not necessarily, because there. So in the SSA form, you might still have these little dead zones, right? So you can have a dead zones where something just overlap in this little region, and you really want to stop the live range and continue after a different point. So I don't think, remember that problem that we look in here. Find it. Yeah, like this guy. So I don't think with. Yeah, so Albert also sent an example. Yeah. So you really don't want the situation where activity happens in the 2 line and they had overlap over 100 lines. Yeah, so it had like huge overlap in live ranges, right? So it's not about whether it's SSA form or not, right? It's just overlapping, and that can be 2 lines, like as in this example, but it can be hundreds of lines, right? So you can have a humongous degree, you can just tremendously reduce that degree, right?
Okay.
And those degree and this number of lines can happen. Sometimes you don't even realize it happens. You have a function call, and that function call happens to be inlined. So someone inject like hundreds of lines of code, right, into a single place. So it feels like an F call for you, and that F function calls a lot of code, right, into it. Yeah. And then artificially, it would make 2 things that should be close in the code, but there's just a function call between them, like extended dramatically, right? And then they're going to overlap with all the variables in that function because they live across the beginning and the end. You had like A, B defined, and function call, then A plus B after the function call, right? So those things try to fix.
Why global variables are bad.
Yep. That's why global variables are really bad. Yep. Okay, any other questions? Again, I had to be honest, we just scratched the surface. This is the topic. There were hundreds of papers published, multiple theses published, right? So multiple people's work on that since probably 60s, if not 50s, right? So it's a very, topic, and it's still important. So like, it's not like the problem that's gonna go away in the near future, or there's expected a solution there. So people still try to improve things in different contexts. Okay, so we covered that. Now we're going to talk about something related, which is called register coalescing. So what's that? So what we're going to focus on is the copy instructions. So remember, usually we were saying, well, we inject copy for this and copy for that, but don't worry, when time comes, there will be copy propagation, register location, copies will go away. This is partially true, but only partially. So certain optimizations can optimize away copy instructions, right? Because they feel wasteful, right? Like if you look at copy, why just don't replace it with this thing, right? If there's y equal x and y is used here, why just don't use x directly here? And in many cases, it can be done. You do first a copy propagation of this x into here, and then you do that code elimination. You delete this instruction. Here we go, copy is gone, right? Sounds like no problem, but the question is, can all copy instructions be eliminated using this pair of optimizations? As you can imagine, if the answer would be yes, there would be nothing to discuss in the next 30, 40 minutes. So the answer is unfortunately not. And here's the reason why. So here's a copy y equals c, here's a copy y equal x, right? Typical hammock we have. And then there is a y here. Can we copy propagate it or not? So as I see, you probably see now that it's not easy, because depending on how you went, it can be both c or x, right? So there's no easy way to copy propagate things. So use of copy target that has multiple conflicting reaching definitions cannot be done in a straightforward manner. There's another example where the copy instructions remains. For example, here you have y equal x, and there is a y in here, and there is another y here, right? So you can substitute x for y in here, but you cannot do it here. So that substitution doesn't really buy you anything, right? Because you don't get rid of the copy completely. So copy target y still live even after some successful copy propagation happens. So you might copy propagate certain things, but it doesn't guarantee that it would remove the copy completely. So the bottom line, copy instructions may still exist when we perform register allocation. And remember, some of them will be generated by things like SSA and a lot of other optimizations that we do, right? We're going to generate a lot of copies in many different cases. We generate copies when we're removing variants outside of the loop. So we generate a lot of copies ourselves, right? That's common. So they had to be removed because otherwise they're real instruction they're going to, you're going to spend time on. So how are copy instructions and register allocations are related? Well, let's challenge you again. What a clever thing the register allocation can do to just eliminate the copy. So imagine you have y equal x. What the register allocation can do to get rid of that? It's very simple, think about it. So what register allocation can do to get rid of this thing?
Assign them to the same register.
Exactly. R7 equals R7, right? So register allocation has a lot of power, right, to deal with these copies. If we can assign both the source and target of the copy to the same registers, then we don't need to perform the copy, right? It would be just removed. And even though the optimizer was not able to do this, register allocation has the power to actually perform that, okay? One way to do this is treat the source and target as the same node in the interference graph. If we can do that, then the coloring algorithm will naturally assign them to the same registers, and this is called coalescing. So essentially, I would make A, Y, and X treated as kind of the same object, right, in the interference graph. And if I keep them always the same, it means they would, by design, get the same color assigned, right? Because the problem right now, if I would just run register allocation randomly, there is a high chance that Y and X won't get the same color, so I cannot just make them R7, right, like optimization. But if I make them the same color, then it would be great. Do you smell like there's some problem here if I just go for that? Like, it's not straightforward, right? I cannot just always do it. Why? Why is that? So if I go for that approach, what's the challenge? I take two nodes and I fuse them. So what happens? Anyone see anything dangerous with fusing two nodes into one? Why wouldn't I fuse everything into just one node in the graph if I can fuse things?
You might want to change them independently later in the code.
Not necessarily. Like, the only thing I do here is just say, well, this can be interpreted like, when I make Y and X one node together, what I say, I make a restriction into my coloring scheme that these two things has to be the same thing, right? I add a restriction. What also happens is that if Y has a degree of, say, 10, and X has degree 11, when I fuse them, out of a sudden, their degree can be 21. So out of a sudden, I create a node with a humongous degree. So I might make something that was colorable with, say, 15 colors, not colorable anymore. So remember that fusion is not free. I can break colorability. So that's an important thing. So let's look at some simple example without coalescing first. So you had x equals something, a equals 5, y equals x, b equals a plus 2, blah, 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 return. I had x, y, a, b, z. This is my interference graph for a interfere with x, right? I think it's clear why a interfere with x, right? Def, use, right? Then y interfere with a, y interfere with b, and we had a valid coloring with 3 registers, which is not hard to find, right? Without coalescing, x and y end up in different registers, right? That's the problem. So that won't eliminate the copy instruction. So what we do then is we make them the same node, x/y, and that's the graph we get. With coalescing, x and y are now guaranteed to end up in the same register, and the copy instructions now can be eliminated. But we cannot do this for every single copy, right? Because it might cause us some trouble. In this case, it didn't, but in other cases, it might. So let's look at this example. Should we coalesce x and y in this case? So I had y equals x equals 2 here, and the use of y and x in here. Question for you, should I coalesce in this case or not?
Should not.
Why not?
Because x changes, but y still remains at the old value.
Yeah, essentially, this is actually going to break correctness. So if I actually going to do this here, that would result in incorrect behavior if this branch is taken. So it's okay to do it here. You'll get x, 2x, but here it's actually a different meaning, right? So it's only legal to coalesce x and y if and only if initial definitions of y's live range is this copy instructions and the live ranges of x and y do not interfere otherwise. So the only interference between the two live ranges should be happening on this copy instructions and nowhere else. If the copy is actually a required copy for the meaning of the code executions, you can do that, right? So it means you can do this for some artificial copies that only had like a one use, and that's the only use. Like the copy exists only there for renaming or something. But if it actually has a meaning, you can't just do that. So first of all, the problem is correctness. But remember, as I already hinted you, just because it's legal to do it, it doesn't mean that it's always a good idea to do it. Let's look at the examples why coalescing might be undesirable. So we had x equals a plus b, y equals x, and then z equals y plus 4. If you look at this code, there might be a huge space in between these things, right? So something similar to what Albert already shows you in another example, right? So if that happens, when I merge this x, y, and 2, I'm going to create a live range with a huge span, right? That's going to work like several hundreds of instructions. That's going to interfere with a lot of things. How is it going to affect colorability of the interference graph? Well, it might be quite negative. So fundamentally, what coalescing will do, it would add extra constraints to the colorability problem. So it doesn't make coloring any easier. It makes it more difficult. You might get rid of the copy, but at the cost of coloring being more difficult. So if we coalesce in this case, we might save a copy instructions by get spilling. Remember, spilling would go to memory. So one copy, if this copy between registers is going to be a cycle or something, right? And we might add something that would be 100 of cycles. We really don't want to coalesce if it causes extra spills. So as you can feel after that, our strategy during the rest of this lecture would be trying to coalesce, avoiding the negative effect on coloring. So we're going to use some relatively straightforward heuristics that would allow us to do coalescing without hurting the coloring algorithm, right? So we don't, one of the key idea here, we cannot know what's colored or not. That's complicated. But if we can prove that after doing that, the coloring is not harder than before, then it's good enough. I don't need to prove that it's colored with that color. I just need to make sure I don't make anything worse. That's going to be the goal. Any questions so far? So I hope you see why the coalescing needed. You see why it's not trivial, right? Why it requires some thought into that. And the importance is also clear because the number of these copies is humongous. If you're actually going to go without optimization, there are going to be a lot of these copies because a lot of optimizations generate these copies. So, okay, the when to coalesce, obviously the goal, it has to be legal. We only want to coalesce if it would make colorable, we want to coalesce unless it would make a colorable graph non-colorable. The bad news, as I said, predicting colorability is tricky. Depends on the shape of the graph. Graph coloring is NP hard. So let's look at this example, for example. You see A, B, C. This is an interference graph for the 6 variables. And assuming 2 registers, should we coalesce X and Y? So the original graph was 2 colorable, right? That's the coloring scheme that would work. If I mix X and Y together, would that be 2 colorable? Remember from the theory, you easily find a subgraph like that, right? And you can say that, yeah. So it's not 2 colorable. You get this subgraph here, right? So how we can represent the coalescing candidates so that we somehow distinguish them from regular nodes. So instead of just fusing right away, you kind of want to delay. Remember, similarly, like lazy strategy here is actually quite good. You want to delay it. So what we do instead of coalescing them right away, we actually create a special dotted line that represents coalescing candidate, right? That's a new type of interference edge. And we try to assign vertices the same color if we can, unless it becomes problematic, in which case they give them different colors and we give up on the edge, right? Okay. So solid lines, the regular interference, dotted lines, candidates for coalescing. And vertices must be assigned different colors, okay? For example, here we would actually can figure this out. So how do we know when coalescing will not cause spilling? So that's the first problem, because the spilling is the problem, right? The spilling is a very costly process. Remember, we're just getting hundreds of cycles in a place that was just a few cycles. Recall from the coloring algorithm, we can always successfully n-color a node if its degree is less than n. So to ensure that the coalescing does not cause spilling, we need to check that the degree less than n invariant is still locally preserved after coalescing. The key thing is locally, not globally, right? If so, then coalescing won't cause the graph to become non-colorable. So there's no need to inspect the entire interference graph or do trial and error, because that's all very expensive. So remember, we do not need to determine whether the full graph is colorable or not. Just need to check that coalescing within this piece of the graph does not cause a colorable graph to become non-colorable. So the first simple heuristic, if the degree of X plus degree of Y is less than n, so no problem, right? I just fuse 2 nodes that has a very small degree. The total degree of a joint cannot be larger than the individual degrees. So that's very simple. So for example, if we have X and Y having this graph, we just check that and the sum is less than 3. So if the degree of coalesced node can be no larger than 3, essentially, right? So if n is bigger than or equal than 4, we can always safely to coalesce these 2 nodes, right? You see these dotted lines here. What it means, there are some other graphs here, but the cool thing, I don't need to know about it. I can make that decision just for this edge by just looking at how many edges it has in the graph overall, the degree of those nodes. And I can make the decision coalesce or not. So if n is bigger or equal to 4, there's an answer here. But if it's less than 4, it's unclear, right? because that heuristic doesn't work, okay? But this is the first easy thing, right? Like a lot of cases can be resolved like that. So how can we safely be more aggressive than this? Because that seems to be a very simple heuristic. Let's look at this example. Assume n is equals 3. Is it safe to coalesce x and y here? Let's look together. So you see x, y here, you have these things, right? As you can see, the sum of x and y is just 3. So we cannot use the previous heuristic. But you notice that x and y share a common interference neighbor of A. What does that mean? When I'm gonna look at when I actually computed their potential degree after coalescing, I overcount. I count this thing twice. I had X having this edge and this guy having this edge. But after I fuse them, that edge is not going to be replicated. That would be just one edge, right? So it means I don't need to double count the nearby edges. So hence the degree of the coalesced node is actually going to be only 2, not 3. And then coalescing is guaranteed to be safe even when n is equal 3. That's another trick, right? In our bag of tricks here. You see the beauty of it. It's still local. I don't need to go through the whole graph. I can just locally inspect my own edges. If there are common edges between x and y to the same node, right? That means that should be deducted from your degree. So I ask here, how can inject the algorithm to capture that? It's relatively straightforward, right? You can just deduct the common edges. Another helpful insight. Colors are not assigned until nodes are popped off the stack. So nodes with degree less than n are pushed on the stack first. When a node is popped off the stack, we know that it can be colored. So because the number of potentially conflict neighbors must be smaller than n. So spilling only occurs if there is no node with degree less than n to push one on the stack. So let's look at one more trick. So another possibility of handling things that might have very high degree, but if that graphs that x and y deal with has nothing to do with each other, then despite the fact they can have a high total degree, they can be still, nicely spilled. So the question here, say x has degree 5 and y has degree 5. Can this graph be too colorable after we coalesce in x and y? If we just do 5 plus 5, we go 10, and the answer would be, well, probably not. It's too colorable and I had degree of 10. But the thing is, all these nodes here actually has nothing to do with each other. So I can actually safely to color this graph. So how we can build something based on this aside? So when would coalescing cause the stack pushing to get stuck? So coalesced node must have a degree of larger than n, then we would create a problem. Otherwise, it can be pushed on the stack and we're not stuck. So how can avoid being stuck? And another thing, it must have at least n neighbors that each has degree larger than n. Otherwise, all neighbors would be able to be pushed. So essentially, to coalesce more aggressively and safely, we need to exploit the second requirement. We need to look at all your neighbors and check whether all your neighbors have degree larger than n. Because if all your neighbor has degree larger than n, then it's probably nothing you can do. But if all neighbors has degree less than n, they all can be pushed before that node. Reordering in order in which the nodes are pushed would allow us to push these guys first, and then the nodes can go into as well. So essentially, if we want to do the most aggressive form of coalescing, we need to look at the degrees of all your neighbors, right? That's what matters, not just the degrees of the candidate itself. So the first order heuristics look at just degree of the node itself, right? Do some optimizations there. The next level is looking at the neighbors. And that's where the algorithm was proposed called BRICS algorithms, which if nodes x and y which proposes that the node X and Y can be coalesced if the number of neighbors of them out of coalescing with degree larger than n is less than n. So I know it sounds very tricky. So what you do, you take X and Y, fuse them, and then count the number of neighbors of them that has degree that is high, right? Higher than n, because that's what matters. If the number of these neighbors is not too bad, is less than n, we can handle them because they will get onto the stack before this guy, which means the edges will be removed. Remember, when you do coloring, you take node with degree less than n, put it on the stack, remove the edge. Every the guy like that will remove an edge here, right? So if the number of problematic nodes is less than n, it still can be colored. Why this idea works is because all neighbors can be put on the stack before this node, right? There's always a way to push them. And after that's done, the degree is less than n, because you push all of that, you only had less than n problematic guys. All of them can get their color, whatever they want. And I can still color myself because I had degree less than n. So I can also still go into the stack. So it makes sure that I don't introduce an extra stuck situation in my graph. I fuse two nodes and I make sure that if it was doable, before I could proceed before, I can still proceed, right? I don't introduce any extra stuck position in the coloring. So I fuse, look at my neighbors. If I don't have more than n trouble making neighbors, right, then I can still fuse, right? I can still coalesce. Any questions here? This is a more complicated approach, but do you understand why it works? Any questions? So here I'm showing an example of that, right? So for n equals 2. I look at the neighbors, there's not, no, that's the way it works. I go, first Z goes into the stack, then A goes into the stack, then B goes into the stack, then X, Y into the stack, and then I color. Any questions about Brick's algorithm? I visualize you how it's going to work here. We see there are a lot of neighbors and they all have very small degree. They actually have degree of 1. They will all go into the stack before X and Y, and joint X and Y, right? And as they go into the stack, they will make the degree of X and Y and go down. And that conditions guarantees that after all these guys go into the stack, these edges will go away, and I cannot have more than, I'm going to have less than n edges left because the number of bad guys with high degree is less than n. It means that X and Y, after all these guys go into the stack, itself is going to have degree less than n, and it means it's not going to stuck my algorithm. It's going to let it colored and proceed. I don't make any assumption that I will find the right coloring. There might be still some spills afterwards, but I know I didn't make anything worse in my algorithm. Whatever was okay was still okay, right? I didn't make anything worse. Any questions here? I don't make any assumptions how it will be colored, how many spills. The key thing, whatever was colorable is still colorable, right? I don't make any more complicated situations for the algorithm. But for that, the condition is I need to look at all my neighbors. So if I'm lucky that my neighbors are all relatively sparse, I had two kind of disjoint pieces with relatively low degrees, that trick can be done. So despite that X and Y after fusion have a degree of 10, this graph is still too colorable. Okay, so you see, you can make decisions about coalescing not only on the degree of the node themselves, that's the first order heuristic, but also on the neighbors, right? Okay, and things can go even more, complicated. So one thing, optimizations over Briggs algorithms called George's algorithm. In that algorithm, what we handle is a node with a very high degree, like this. But it's another candidate that's about to merge. Y has a very much smaller degree, right? And say X has a very large live range and Y does not, and we want to fuse them, coalesce them together. With Briggs algorithm, we would inspect all neighbors, both in X and Y, and X has a lot of neighbors, right? So that's going to take a lot of time potentially to inspect every single neighbors. So the question is, if I had the bad guy with live range, can I do better than the Briggs algorithm? I don't want to go for every single candidate here and check its degree. Can I get away with just inspecting Y, not X? So essentially we want to not do in both nodes, but only the one that's easy. Can we show that coalescing makes coloring no worse if we're just given that it was given for given X? So the George algorithms, what it does is it says that coalescing X and Y does not harm if for each neighbor T of Y, either degree of T is less than N, right? Or T interferes with X, right? So this is the only two conditions, right? So either it has a small degree or it interferes with X. Why the second condition matters? Because if it interferes with X, it means there's already an edge there, right? So it means those edges doesn't add anything, right? So this is similar to Briggs. T will be pushed before X1, Y. And the second condition, it means there is no change compared with coloring X. So what we do an optimization trick there. Instead of looking at all there, we just say, you know what? If I'm either like non-problematic by myself, or my problems already in the problems of X, I'm already in there, that after fusion, that edge would be the same, like this edge and this edge will collapse, right? So if every edge is one of the two types, then I can handle the fusion by looking at Y without looking at X at all. So when I'm fusing two candidates, I'm just picking on which candidates I want to do because it's simpler, right, to handle. So I can just handle when I try to interfere two things, when one has huge range and one has a tiny range, I can focus on the small guy. And if it turns that the big guy has all my edges are either non-problematic, degree less than N, always can be colored, or has the same edge as with X, then I'm done, right? I can't do it. I'm not going to make any extra harm. Questions? Okay.
So this basically just saves time.
Yeah, saves time. Yeah. This guy with a huge live range practically can be, remember we try to make all this local, but going for more and more, further and further away from the original nodes, make the algorithm more and more complicated. Yeah. But you're absolutely right. That doesn't make the coloring better. You just try to speed up the Briggs algorithm, right? Questions? Okay, this is pretty much the state of the art of coalescing like 80s, 90s, right? So those are real algorithms that people use. There are probably more sophisticated versions right now, which I didn't check recently. But hopefully it gives you a good impression. After doing register location plus coalescing, you pretty much had most things ready for something called instruction scheduling, right? That's kind of the last stage. After that, you just generate the code, and that's it, you're done. You get the code running, right? Any questions? Those are the register location and instruction scheduling are probably the most two important, stages of the compiler. Like you can get rid of everything, but you cannot get rid of those two. Any questions?
So can I ask the last question? I got myself confused at some point. So like I know that for coalescing X and Y, we might make a colorable graph non-colorable. But is it possible to do the vice, like the inverse, like make a non-colorable colorable?
No. By fusing two things, you only make things worse. You add a new constraints that didn't exist before you, but you didn't make anything better. You restrict things, so you cannot make anything better. You can only make things worse. So you coalesce because you want to get rid of copy, right? And for that, you pay a price. You add an extra constraint. Any constraint won't make anything better, right?
Okay. I see. Thank you very much.
Okay. Hope I didn't overload you. I picked the relatively simple versions of the algorithm so they would make a meaning. You can see how it evolves, right? We're starting with looking why we need coalescing, then we look at the trivial cases, we see why it might be unsafe, then we have conditions when it's safe, and then sometimes it's safe but not profitable, and we build up on when it's profitable. Remember the benefit, here we're dealing with an optimization where the benefits for each copy is tiny but valuable, but the cost of mistake is humongous, right? So essentially, if you coalesce something that makes it a spill, that outweighs hundreds correct decisions, right? You understand what I'm saying, right? Because I replaced something that was a cycle with 100 cycles, right? So if I make something, by making coalesced an extra spill, I just outweighed a lot of positive decisions. So essentially, I have to be very careful, right? I need to be very careful with coalescing, not to introduce any extra problems into click coloring. Okay. So summary. So coalescing can enable register location to eliminate copy instructions. Sounds very impressive. The register location has nothing to do with copy, and optimizations can actually get rid of a lot of copies and help, which other optimizations cannot because it has so much freedom in making different decisions. Coalescing, though, must be applied with with a strong care to avoid causing register spilling. Spilling has a huge cost. So we augment the interference graphs with the special dotted lines for coalescing candidates. So instead of just coalesce everything we can, right, we always carefully do it. Remember, we could actually coalesce everything. That would be a very, problematic graph with a huge degree that we never can color afterwards. We cannot color obviously unsafe things, but we can color a lot of things that are safe and get still a terrible graph for coloring. We try to allocate to same registers unless these may cause spilling. So coalescing algorithms simply based on degree of coalescing candidates nodes X and Y. I show you very simple heuristics such as total degree X plus Y less than N, right? That clearly can do it. Another thing, the same thing X plus Y by taking repetitive edges into account. So essentially X plus 1 minus the set of repetitive edges. If it's less than N, you can still do it. And then we come up with an algorithm or describe the algorithm called Briggs algorithm, where we look at the degree of neighboring nodes of X and Y. And by looking at them, if they had low degree, if they're not problematic nodes, then we can actually fuse. And even if the total degree is high, it might be still colorable, right? Because the other peripheral neighbors had a very light degrees. And there is George algorithm, which is asymmetrical. It's an improvement of a Briggs algorithm that try to avoid looking at the node with a huge interference graph, right? A lot of edges, focusing on the neighbor that has a very lightweight. So it would make the Briggs way more efficient, right? So it's essentially, instead of complexity where you would have to look at all neighbors of X and all neighbors of Y, you would just look at, and essentially if there is significant disparity, so instead of doing a linear search on a large number of neighbors, you're just doing a search on just a few neighbors of Y, right? So if there's big asymmetry in the graph, and that all practical, but probably people observe a lot of this graph, where there's something with a huge life range and something with a small life range. Okay, that's pretty much what I have for today. Any questions? Okay. Okay, so if there are no questions, then yeah, please start to prepare for the midterm next week. We'll work on it with Bojan, and we will release probably some details this week. If there is anything special you need to know about the midterm, about the length and everything. I think I already said probably around 80 to 90 minutes, not longer than that.
Sorry, I remember the TA mentioning that this lecture might not be part of it. Did you say it will be part of the midterm?
So what we usually do, because every year sometimes we do have that lecture before the midterm, sometimes after. So there might be some simple questions related to register allocation, but not like big problems related to it, right? So there's going to be a section with like simple questions, right? You know, multiple choice questions that can be from this lecture. But the big problems will be focusing on the early lectures.
Okay.
We didn't finalize the midterm yet, but that's my honest answer. Like, I'm not going to put any register allocation problems as a big point problems, right? But there might be some simple questions about it. Okay. Any other questions? Okay. No questions. And thanks a lot, guys. And see you next week. Bye.